Alright guys, so today we have Codeforces round 710 for Div 3. I've been away for a while, but so yes, I kind of missed several contests. I still don't know what we're going to do about them, but I definitely want to solve them at some point. But today we have Div 3 round, so um, once in a while I have enough free time for it. Let's do the problems. Problem A, strange table. We have a rectangular table of n rows and m columns. Each cell of the table has its number obtained by the following algorithm by columns. Okay. Cells number one. Okay. This cell number by rows is number by column. Okay. So if we have rectangular table, we can basically enumerate the cells of this table into two different ways, one of which is by columns and the other one is by rows. And what we want to do is we want to given a number of a cell in like one enumeration, we want to tell the number of the cell in the other enumeration. So basically we want to have a way to convert the ID of the cell into row and column, and then back to ID uh, in another enumeration. And because n and m are kind of large, so we don't want to like create in a n times m table. What we want to do instead is the following. So let me read the input, right? Sure, we have std div, which returns the quotient and remainder. Just let me think, what do I want to divide by what? I clearly want to subtract 1 because it's not nice to have it. I am given by columns, right? So I should divide by the number of rows. It will return a pair. I can unpack it. And what I want to print, one line, is by rows, right? So the row should get multiplied by the number of column. Oh, actually, yeah, you're right. If you spotted that mistake, I believe I want to output something like that. Where we only have one test file for that problem, sample test case. So 1, 3, no, something clearly went wrong. I want to divide. Maybe these guys can just swap around. Yeah, apparently they are. Whatever. Like we divide with remainder because if you look at some row, you notice that once you subtract, like all the numbers in one row have the same remainder when divided by number of rows, obviously. So that's why we're interested in remainder, and then column is just the quotient. So we can use std div for that, or we could divide explicitly, but why not? Why don't we use a standard function for that? Problem B, yeah, and we got accepted in case we missed it. We have, oh, we should, yeah. Oh, we should accept. Problem B, partial replacement. We're given a number k and string s of length n consisting of the characters the dot and star. Want to replace some of the star characters with x characters so that the following conditions are met. The first character star in the original should be replaced. Okay, the last star should be replaced. The distance between two neighboring replaced characters x must not exceed k. Okay, so minimum number of stars to be replaced. Could do, no, I mean, what? It looks like the greedy should just work. Want to replace the farthest x, the farthest star, which is not farther than k. Yeah, I don't see a reason for greedy algorithm not to work. So we'll just implement that. In case it for some miraculous reason fails, we always have binary structure with an answer. But I don't think it's necessary here. Okay, did I bet the, yeah. All right, then it looks like everything is kind of short. I am not sure. Yeah, no, legitimately, I'm not sure what happens. Like, um, right. Maybe that's just an implementation problem. So we will just be as explicit as possible for that kind of question. What we do is we just look for all characters of the string, check if they are a star character, and if so, we push back to the vector of star positions. And I'm pretty certain that you can implement a linear time algorithm for that, but I think it was not expected from us. So what we're gonna do instead is going to use the dynamic programming approach. Also, and it feels like I'm pretty stupid for some reason. Like our equivalent is it or something, but whatever. This. So we're going to loop our previous position. That's literally what they said in the formal description right here. Semicolon positions or symbols on but the only difference being that we don't compare G and I directly, we compare star positions at I and star positions at J. And I can just slide it in here. Or actually, yeah, technically it makes more sense to loop this way, right? Should be as right? So we loop the other way. We're trying to find what is we loop as long as previous position is correct. And I really should type J here. That's one reason why in serious programming people like don't use one variable, one character variable names. We are trying to do something better here. So, all right, looks legit. I mean, I should just wait DPI gets minimum. DPI really should. Yeah, I mean, we always can replace just like that. If I take the current character, right? So dpj plus 1. I have to do this. That's fine. I don't know. We should try to implement like linear time algorithm for that. Answer that. If we solve all the other problems, we may consider doing it linear time. Let's check current cases. Okay, and our boss at least one. It's guaranteed that there is at least one star. Neighboring does not exceed K. This like literal says that, yeah, like nothing can go wrong, really. I don't know. Strings are not long. I really see no reasons for it to fail. It's kind of sad. Like, probably be basically have to implement something instead of actually thinking, well, that's expected, I guess. We got accepted. So let's just get to problem C. But I guess like this kind of problems are something that you can actually see like in real life, in case you are not like developing database management systems or something like highly intellectual, then maybe you see some problems like this. But more likely it will be like class structure, I don't know, system design, something like that. Problem C, double-ended strings. When given two strings A and B consisting of lowercase Latin letters, we can do n number of the following operations in any order. If string A is non-empty, we can do it the first character of A, and yeah, okay. If it's non-empty, do it the last character. So basically, A and B are double-ended queues, so B queues. Dex. I believe we'll just say Dex. So what do we want actually? Do we want to equalize them? Yeah, okay. Up to 100 test cases, up to 20 times 20 times 20 times 20. I'm not all that good at counting, but it sounds kind of stupid. What the heck? Yeah, whatever. So you can basically, because strings A and B are very short, you can just loop over all possible substrings. And the only intellectual move, kind of intellectual, that we're going to make is instead of looping over all substrings of A and then over all substrings of B, we're going to store all substrings of A into a set. And then for all substrings of B, check whether this substring is in the set. So kind of meet in the middle approach. Let me just implement what we mean by that. We'll see. So the actual complexity will be like around 20 choose 2 times test cases. So it's like really cheap. Map set vertical sets. Do I have to count in case of strings? I don't think it's going to be hacked. Not on this number of substrings. So A substrings. Just moderate set of strings. What are you doing next? Yes. Oh, of course we need that's also string, right? And then what we do is we just write nested loops. Actually, inclusive or exclusive? I want exclusive. So this one with this one. So what actually is going on here is that we have half open each one, like left, right. And that's all we do. A substring from left, and the length will be just right minus left. Because I chose this to be half open, I can verify that the length of the string is just right minus left, instead of like right minus left plus 1, which would be the case if right was included. But it's not, so that's it. I assume that we also want to include empty strings, actually. For whatever reason. And because A and B may end up being empty, right? If they don't have common characters, then there is no way we can make them equal. Well, okay, I admit, yeah, you're right. If you spot me, I said that the only intellectual thing we're doing is this kind of meet in the middle. Well, in fact, we're doing another non-trivial observation, which is, of course, that every substring, no, actually, like the string without some prefix and suffix is basically any substring, right? This sometimes helps with subsegment query problems, right? When you want to yeah, that's kind of non-trivial part, so let me finish this. Yeah, so like sometimes you want to process some queries, range queries, and you don't really want to implement like complicated data structure, like segmentary or something. And sometimes you can get away with just some prefix and suffix data structures. Why would you ask? Because, in fact, like every subsegment is like entire array minus prefix minus suffix, and sometimes this observation helps a lot. I don't actually like way I did it, so I need to rename minimum operations for maximum count. Well, as you can see, I'm basically going to leave it this way. Simplify. So what actually goes on is that what is the number of operations, minimum number of operations that we need? Is a lens plus b lens minus max common, right? Actually, if we do it like that, even, then we can just apply the 2 times max count, right? Because it corresponds to something like that. So you got to delete that many characters from A to get this maximum common part. You got to delete that many characters from B to get to the common part. We know how this compile string is just above my head in the recorder. 0 to 13,320. I guess this is what we wanted to see. And then we don't actually need this part because we always say max common of 0 is possible. Just to make it sure that I did not break anything. Should see the same numbers. Let's see if we didn't do any stupid mistakes. No. And apparently the time is 0 milliseconds, whatever. I'll take that. Yeah, I think that nobody just no, the constraints are really low. Maybe that's the reason. Okay, and now we should get to the more interesting problems, like div3d may be div2a, I believe. So we should get more focused for this purpose. Of course, drinking tea helps. Oh, that's actually hard. I expected it to be colder by the time we finish all the simple problems, but now it's still hard. So we're given an array A of lengths n consisting of integers. We can apply the following operation consisting of several steps on the array A, 0 or more times. Okay, so 0 is important. So we may select 2 different numbers in the array AI and AJ. We remove both elements. Okay, so we can remove 2 different elements. So here we can remove like 1, 6, 1, 4, 1, 4. Minimum basic. No, wait, that's kind of sus. I mean, majority minus half. And then if majority is smaller than half, then just what? Am I stupid or something? Oh no, wait. If there is no majority element, then we can always, well, all right. So Because we delete in pairs, if n is odd, then it will always remain odd, right? So we'll never get to 0. That's kind of unfortunate. But other than that, I believe that basically our question is the majority element. There is a majority element, say, let's say we have like 20 elements and 13 of them are equal to 7. And clearly we cannot get rid of all 7s because there are just too many of them. And what we don't want to do in such case is clearly pair all 7s with all other numbers. And then we'll 2 times majority count minus half the array will remain, or 2 times majority minus length. I don't want to divide by 2 in case it was odd. Yeah. So anyways, and like the interesting part is why we actually can I don't trust. Okay. For obvious reasons. I really should just use GP hash table or something that's not quadratic. But yes, map also works. It's kind of equivalent to sorting the array in total length. Yeah, it should be fine. Just believe in it. And this is going to be a bit faster this side, but I don't think we need it. Like the more interesting question is if we always can. If it's true, is it true? Is it like if we don't have a majority elements and we can always get just the pairs of elements? And I believe it is true. I really do believe. I don't really want to prove it. So let me see. What would be the easy way to show it? Not in X frequency, but in M. Well, what would be the way to prove it? All right. Suppose, yeah, make arbitrary pairs. Suppose you didn't succeed. Like then why you didn't succeed? What you didn't pair all the elements. So suppose why you didn't pair them like with themselves. It's either because there is one of them, in which case you actually succeeded, like because we already talked about the odd even case. In the other case, there are 2 equal elements. And you just take, if any other pair contains this element, then this is a majority element. Otherwise, if you can break in pair and just pair these 2 with these 2. You increase the number of pairs. So yeah, the solution is indeed based on the majority element. And what all we want to do is compute 2 values. Majority lower bounds is going to be max frequency. 2 times max frequency minus m, I believe. Why is that? So if we have like 13 sevens in the array of length 20, and there are 7 remaining elements, and the difference is 13 minus 7, which is 6. And it's the same as 2 times 13 minus m. And this is the lower bound on the number of elements that can remain because of the majority element. Notice that this value may be negative or 0. And this is okay for the lower bound. Then we have also parity lower bound, which is simply equal to m bitwise m as well. So this returns 1 if m is odd, else 0. And then like we can just take maximum of these two guys. So you never can be too sure. Yeah. Yeah, it's a bit a habit from work. Just make everything that you can make const, just make it const. So let's see if this actually works. 0, 0 to 1, 0. And I believe it's really like reasonable. We don't have any stupid cases, and there's at least one. AIs are integers. We can probably spin this thing up, but we don't need to because some of them is small and this complexity is elegant overall. Yeah, well, let's just make it. Let's see if it passes. Yeah, it's acceptable. Not the fastest solution out there because of the map, but you don't want to get hacked because an ordered map is quadratic, so that's why we use map. I actually took less time to implement these in C. Now we should get some more interesting problems. Am I right? And I also noticed that there are 7. So, I wonder if we're going to use our drawing tool, because we didn't do so far, but maybe we'll. So, yeah, finally, problem. You can tell when it gets harder by the fact that no, it's actually yeah. I'll tell you. Never mind. Should be just. I thought for a second there are multiple input files, and I thought like multiple sample tests, and I thought, yeah, now we are talking serious, but no. Problem E restarts permutation. I wonder if there is like at least one subscriber out there who likes permutation problems. I doubt it, but let's see. Maybe it's not a real permutation problem. I have permutation. Yeah. Permutation. The permutation turned into array Q according to the following rule. Qi is the maximum of P1 to Pi. Lexicographical minimum and lexicographical maximum permutation could be presented to him. All right, so some positions get restored immediately. Like the positions in which maximum changes are we can clearly restore them. And positions where as we restore these values. Yeah, I bet we can just simulate like if we put all the remaining elements into a set, then we can just lower bound, upper bound on it, and it will return what we wanted. So let's check it. And the idea is that after you restart some positions, it got to be something. The remaining integers have to be slotted in according to some rules. Oh no, I was wrong. What is the way to do it then? I legitimately don't know yet. Oh, we'll see. What would you want to do this? So what we want to do is if well, technically yeah, we're going to write it this way. So this is what happened. Like if the position, if two prefix maximums differ, and prefixes differ by one element, and the next prefix maximum comes into this element. So like when we have 4, and clearly this element is 4 in both maximal and minimal permutations. We restart some positions, right? What do we do next? Have some numbers that were not used. We can just throw them into set. And I say set because we clearly want to extract maximum and minimum, because maximizing like graphically is the same as maximizing like first element and then second element. So let me just throw everything that was not used into a set. No, this no. We don't write loops from I equals 1. Actually, right. You got to be careful. Oh, no, yeah, right. You want all this. Not sure if this helps, but what like something help. Now we know what numbers were not used. Now it's fine because it's n log n, and sum of n does not exceed 2 times 10 to the fifth. But how do we restore the permutation? Let me see. So we had array Q, which is 3, 3, 4, 4, 7, 7, 7. Right, we restart some position in P. And we don't know what goes here, we don't know what goes here, we don't know what goes here and here. All right. What we can place here is actually like all elements that are smaller or equal to 3. Wait. Right. And when prefer, yeah, I think we just can simulate it. So what we're going to do next is the reason why I do this is because I want to copy vector P and unused. Well, I can simplify it, right? Um, We're going to have different vectors of integers, and we can afford copying P. It's not that much of a deal. That's most. We would need to erase P this way, so you just copy and we'll return P as it. Got our pen. Yeah, everything looks fine, just fine. So like the idea is when we want Lex smallest, we just place minimum element. Let me copy this into. Oh, I am sorry, guys. I'll stop it for a second because I really want to answer that question. So yeah, here we are back. Everyone, when we want smallest, we just insert smallest. When we want largest, we want to insert largest. It's smaller than current maximum. Well, here we actually. If pi is 0, which corresponds to like undefined element, remember that we only fill out defined elements. If current element is undefined, pi gets used. From unused, just like that. Here we will need a bit more work. Current element is undefined. Get and use lower bounds. Lower bound returns first element that is greater or equal to. right? Sure it returns first element that is greater or equal to, so we actually have to take previous of that. Not less than, greater or equal to. What do I want? Graphics max. Is it guaranteed that so okay, so we always can restore some permutation? Like writing like that, we copy, so we don't have to care about what that this erases from the cell that we need here, because we made a copy. I don't know, man. Sounds legit. Let's try it out. Three one four two seven five six 3241 765 1234 1234 3451 276 3452 176 11. I don't know. It just makes a lot of sense to me, and because it was applied to some permutation, it means we can restore it. And I believe that take a maximum or minimum, yeah, pretty much whatever order we just take it and get accepted. Now we have two problems. I'd like to check out how we're doing. Yeah, not really quick, but notice that problem G looks like it's in your F, but we'll see. Not particularly fast, but then again, yeah, idea is not for me to solve these three problems super fast, but to explain solutions. And I hope that I'm doing a good job with this and explaining. Let's see, read problem F triangular pass. We have an infinite triangle made up of layers. Let's number the layers starting from one from the top of the triangles from top to bottom. Okay, so first number is layer, second is again layer. Escape points, number three, infinite triangles. So far sounds like a Pascal triangle, or no? Binomial coefficients triangle. Yes, what do we want to do actually? Do you want me to count paths? Really? No, wait, cost? Also, we do have activated edges. Wow. From this point L1, it's possible to reproduce paths activated edges. Okay. And the minimum cost pass. Yeah, but what is the current activated edges? Oh, this is what I missed. Okay. So if R plus C is even, then the edge to the point R plus 1 C is activated. Otherwise, I suppose that we should just draw this picture for a greater number of nodes and it will become clear. Maybe 5 layers, and then we will be done. Yeah, and then we would just want to find minimum cost path connecting like many points. I believe many points is like the convenient way to represent multiple queries. Without explaining when you connect, like it's our sentence on its own. Yeah, I will just use the regular. So if sum is even, then we go to the left. Because it happens here, and also here. I'm pretty sure it also happens here, and just make everywhere. Right. When it does not happen, like here. Also, here it doesn't happen. Here doesn't happen. Here doesn't happen. So you can already see that we are getting this kind of structure. We have basically like multiple copies of this infinite structure to the upper, to the right. And we want to find minimum cost. That's interesting, actually. See what we can do with it. This is the first number. So once we know all the points, we can get to actually something smart. When the stream, there's always at least one way to traverse all endpoints. From one passing through all endpoints in arbitrary order. Well, there is no arbitrary order, right? Because you always go down. Whatever. Because of that, we actually eventually do points like that. No, I mean, it's going to complain about some used variable easily. Let's just leave it like this. Now we are basically concerned with what is the cheapest way of going from one point to another. Wait. Well, yeah. We also have like initial 0.11. I really want to maintain this. After I sorted this and replaced 1, 1. Up to 10 to the 9, the cost may be quite high. As this kind of tree structure. This is incorrect, of course. For now, it is just going to return 0. For sure. Because there's only one order in which we can actually visit all of them, and it's the sorted order. So we have to sort either way. So we sort it, and we're just concerned with what is the cost from going from a given point to a given point. We are guaranteed that we can go there, right? Let's see what is the cost of going from the initial vertex to every other vertex. Here it is 1, here it is 2, here it's 3, 4. Here it's 0, not surprising. Yeah, I mean, if we start here, we basically can have like 4 sub-triangles, sub-patterns. Then everything is just repeated. This is the same like as this. So we have 4 possible starting points based on if our source row and source column are even and odd. In all these cases, we will return something based on something else. In this case, both are 1 and 1, so we get here. And the costs are as follows. There is a chain on which costs are 0, right? Here costs just increase. Yet here we want to iterate this edge. Cost of getting here is 1. Yet here I want to iterate this edge actually. The cost is 1. To get here, same story. Here 1, 1, 1. Yes, basically like and then it's going to be 2, and then it's going to be 2 again. Yeah, so the sync is that it repeats clearly. And how does it repeat? Let's see. Have this initial start sync, then all these are of width 2. We're gonna have a strip of width 2 of 3, etc. And we just have to compute this accurately. What are these diagonals? Diagonals are R minus C, right? Destination first equals destination second. And this is the first. This is the first diagonal. So we already take care of this one. Basically, want to return destination first minus source first. Else, so here difference between destination first and destination second was 0. No. No. You see, I'm a fool because this difference initially is source first minus source second, and not destination, and not 0. We want to return the difference in this case. Otherwise, we want to take diagonal distance and going to the source diagonal minus destination diagonal. We want to basically return distance over 200. Yeah, well, it sounds legit. I don't know. Sounds legit. This was only 1 out of 4 cases, but yeah, we're gonna make it. It's just a bit. I don't even know the word. Not annoying, just tedious. Tedious is the word. All right. I suppose we start in a different place. Like, what if we start here? And this sounds actually simpler than the previous one. Because if we start here, oh wait, am I stupid? I must be right. There are not 4 types, but 2 types. The one that starts at green and the one that starts at white. This is actually simpler. And we don't want this. What we instead want is really want to take source diagonal. If source diagonal is odd, then we want to do something. And the part that we already did is here, right? And I believe that we want to take destination diagonal easily, regardless of this. Why is that? Because we are going to use it. This can't happen. Actually, this can happen, but then the answer is just 0. The difference here is that this should return this plus 1, because this is diagonal, you see? This is source diagonal, this is destination diagonal, the distance is 1, and the distance in edges is also 1. You can easily do like this, or do this, or do this. And the distance here is still 1. So we kind of add 1 so that when we divide it by 2, we get what we should get. At least it sounds reasonable. Well, this kind of works. And this is not correct. Why is that? I'm going to try it in this case, which actually includes 2. What the? Wait, okay, 4 is the number of test cases, right? Then we have 3. Oh, that's R and C. Okay, so here we don't get the correct answer. Why? Why is it? 1, 1. Should I print mean cost along the way? So that I know when something actually goes wrong. So we added the very last should be the transaction from 2-1 to 4-3. Let's see where these guys are located. 2-1 is here and 4-3 is here. We actually get in the case that source diagonal is odd, right? So we are here. And we say, get me the difference between them. Add 1, divide by 2. Wait, but the difference should be 0, right? We should return 0 plus 1 over 2, which is 0. Just so that I know what to do it later. This tree somewhere. Oh, actually, this is fine. So indeed, we do call cost from 2, 1, 4, 3, and it returns 1. Something like that. I mean, there are better ways to define it, but without. So it does return from A, which I find strange. See, we called. Look at this boss at the same time. We called cost from 2143 to 143. When we computed source diagonal, source first minus source second, which is 1. When we compute destination diagonal, which is destination first minus destination second, which is also 1. So diagonal distance is actually 0. We want to return 0 plus 1 divided by 2, and we somehow get 1. The heck? No, legitimately, I don't understand this. Diagonal distance equals to 0. Oh man, because I can't type, this is destination diagonal, not diagonal distance. Oh. Looks like our adventures are not over yet. So 0, 1, couple of nines is correct, but then the last answer should be 2. And in our case, we get C0, A0, A0, C0, which is apparently incorrect. It isn't because and we really should use space here, right? Just do it when we want it. The angle distance is always non-positive, which makes me think that I want to subtract the other way around. Zero, one, and a couple of nines too. Some project. When we simplify all this, it actually becomes not that complicated. Just two if statements. Right. Now you can see that we are getting the same answers as we should. Let's make it. Let's see if we are right. Yeah, okay, good. That actually took a lot of time changing them, but half an hour, wow, that's a lot. Yeah, I guess this just tedious. This is just tedious. I don't want this anymore. Well, if G is actually easier than this one, then we are in good times. Let me open this. Yeah, well, 200 people already solved F and 250 people solved G. So let's read through G. Maximize the remaining string. We're given a string S consisting of lowercase letters. While there is at least one character in the string S that is repeated at least twice to perform the following operation, we choose the index subject character. Okay, delete the character at position I, replace, yeah, okay. Codeforces, we can remove O, E, C. First we removed all Codeforces. Oh wait, no. Forces, okay. What if forces? What if forces? Lexicographically maximum strength can be obtained after applying a certain sequence of operation, after which all characters remain unique. Oh, that sounds interesting. So we should, like, for every character, we should remove all of its occurrences but one. Then we want to lexicographically maximize the result. Well, that's not trivial at the first glance. We then don't even bother giving us the length of the string. So, yeah, so this sounds interesting. I'm going to take a short break because, you know, drinking has consequences. And then I'm going to be right back. All right, so I'm back. I was thinking, I noticed the usual time limit. Maybe it's going to be a bit tight. But what I'm thinking is, like, as a result, at most 26 characters are going to, the S will consist of at most 26 characters, right? Because they got to be unique. So what we can try to do is, like, if we know some supplementary information about S, like first and last occurrence of every character. Yeah, I think it's best implemented with a recursive function. That's what we're going to do. It's fine. Don't worry about all that now. Also, I should do something like that. What I want to know is first and last occurrence of every character that is present in S. And why is it going to help me? Because I want to check for each character whether it can be the first in S. How am I going to do that? Well, that's simple. If I know first and last occurrence of every character, then oh, that's actually wrong, right? I should really ask like this. If there is no information about this character, it just gets I. Otherwise, it gets nothing. And here, last always just gets I. Yeah, so we computed first and last positions of every character. Now, why is it going to help us? I want to check what is the largest character that can be first, because the length of the resultant string is always going to be the same. So it's basically we are finding the biggest permutation. The biggest permutation is just maximizing by the first string. And actually, the lexicographic maximum is maximized by the first element. So I'm trying to find the best first character. Now, after I find the first character, I'm going to remove all of its occurrences. And also, maybe I will remove some other information based on based on whether I succeeded or not. No, based on like, do I have to remove something from the prefix in order for this character to become first? I'm going to make it most 26 recursive calls. And each of them takes linear time in the length of the string. 26 because I remove at least one character at every iteration. So it's questionable, but I think it will be fine. So if K2 is not equals to K1, no, basically if V2 is smaller than V1, there is a character which the last occurrence of that character is before the first occurrence of our characters, and there is no way we can do it. It's impossible gets false. Now, if possible, max possible, that max of max possible, and key one plus a, because this is character. Or I really should just make them from character, but I'm not sure how my roadmap works from characters. I think it works fine as long as you provide readable characters. But maybe I'm wrong. We'll fix it later. Now we found max possible character. And we should just take its first occurrence, right? So it starts from first max possible. We guarantee that something is going to match this, and this something is going to be at least 8, so we are fine. Up to n. If string cat I is not equal to max possible, res plus equals si. Actually, like first and last positions, I think can be recomputed more efficiently. But this should work as well. I mean, 26 recursive calls is not much. Oh, I actually already calculated. Oh, so. Well, we exited because of something went wrong. What actually went wrong? Oh, it should be SI, of course. Yeah, as I was removing this part, rewriting it, and I rewrote it the wrong way. ODFRSS, which is correct, is a KMI, CBA, convex hull, wait, WFL DJGPAXS, my now CKTXQJPZ. That was absolutely worst pronunciation of English alphabet that you've ever seen. Ever heard, I should say. Let's see. Maybe it's a bit slow, but I believe it should not be like two. No, it's just done. Well, in theory, we can get hacked still, but it's not likely. So we are just done with that content. Oh, why did I close it? This is different system. What do I want to remove? Object files, graph files, and files. All right, yeah, I'm good. Well, of course, I can't publish it to GitHub, not yet. You can see the standings. So well, that's not bad. I mean, Matthias Landokov did very well in Gala. Congratulations. Yeah, like 1 hour. No, actually, with resignations. These 5 problems were very fast. Second thread, writing in Kotlin now. Must have had a break of some kind. I don't know. Yeah, so this was not bad. I hope we don't get hacked. Well, we should not, because like we didn't do anything stupid. So I guess it was it for today. Thanks for watching. I hope I will upsolve the contest that I missed. If we check the full length of contests, and unfortunately there will be like a lot of missing contests for me. No, this should actually be solved. Yeah. So I missed a fair bit of them. I will upsolve this part, but I'm not sure about the formats. So maybe it will be more interesting if we actually do some streams instead of like pre-recorded videos, so that I can solve these problems with you kind of being able to ask your questions whenever you get some, and not after the recording gets published. I don't know, we'll see. Yeah, anyways, it was it for today. Really hope you enjoyed. I guess this was kind of informative. Well, at least we solved all the problems, right? And I also don't see a stream by some LGM explaining all solutions, so probably it's going to be like, well, yeah, should pass solutions. But I mean, it's never bad to have 2 solutions. 2 editorials. So yeah, that's it for today. See you next time, hopefully tomorrow, but we'll see. Bye-bye.